Hey everyone. Yeah, I kind of got cut off. That's what happens when I go on and on, right? Anyways, my point, this is part two now, guys. Okay, my point being use your judgment here. If you get 1.4999, that's basically 1.5. So go, if you need to, go 1.5 math fraction, and you get 3 over 2. So your answer would be 3 pi over 2. Okay, so we have three solutions. Okay, we've got them exact values now. And we want to state the general solution to the equation. Okay, so if you think back to the last lesson regarding general solution, okay, so sometimes it's easier to look at this, pi over 6 here, 5 pi over 6 there, 3 pi over 2 here. So essentially what we can do is add, I don't think these are all the same distance apart, maybe they will be. Hang on, we'll write down our possible answer first by going pi over 6 plus all the way around 2 pi n, and then 5 pi over 6 plus 2 pi n, and 3 pi over 2 plus 2 pi n, all the way around where n is an element of the integers. Okay, so that would be an okay solution. I'm just thinking, I'm looking at this wondering if these guys are all the same distance apart. Let's just try this out. If you go 5 pi over 6 minus pi over 6, right, figuring out this angle here, we would get 4 pi over 6. Let's try going 3 pi over 2 minus 5 pi over 6. Okay, so that would be this angle here. So we need a common denominator. Let's multiply this one top and bottom by 3. So 9 pi over 6 minus 5 pi over 6 is 4 pi over 6. Look at that. And of course it's symmetrical, so this one would also be 4 pi over 6, or otherwise known as 2 pi over 3. So guess what we can do on this one? We could actually name this with one angle. So instead of that, let's write x equals, start with your first angle here, pi over 6, plus, how much did we add to get to the next one? 2 pi over 3. And that carried us to the next one and to the back to the start again. So if we add multiples of that, throw an n on there, where n is an element of the integers, that is way more succinct way of writing it than what we have with the 3. Okay, so if you spot that, definitely go with that with our general solution. Okay, good job. Let's look at the next page. Okay, example number 3, we're looking at basically that same equation we just found the roots for graphically, but now we're doing it algebraically. Okay, so a little bit trickier, but we know what we should be getting, right? Let's write this equation down. Now, notice we have a squared on our sign, and we also have another term that has sine x. So we're going to actually, this is a quadratic equation is what it is. So we're going to bring everything to one side. If it's a quadratic equation, you want 0 on one side. That's our first step. This is from 20-1, so hopefully y'all remember that. 0 on one side. And then you want to factor if you can. Okay, I don't think we'll have any with quadratic formula at the 30-1 trig unit. So we'll add sine x to the other side, add sine x to both sides. Okay, you can't add it to sine squared because that's not the same type of term. So plus sine x, subtract 1 to both sides, and we should end up with that. All right, now if it's easier to look at by replacing, say, sine x, so we're going to let sine x equals m, then we're going to do that. If you find you can factor this without doing that, feel free to do that, okay? So we have 2m squared, right, plus m minus 1 equals 0, okay? And then we're going to do our two sets of brackets, okay? And if you recognize, we have a 2 in front of our m squared, so this is our funky weird factoring. So we're looking for two things that multiply to negative 2. Okay, first write 2m, divide by 2, sorry. So two things that multiply to negative 2, add to positive 1 would be 2 times 1, only two things multiply to 2. We want positive 1, so plus on the 2, minus on the 1. Okay, so 2m plus 2 is like writing 2 bracket m plus 1 if we factor that 2 out. And the 2 will divide, and we're left with m plus 1 and 2m minus 1. And there we go, equals 0. So we could replace sine x back in right now for m, but you know what? It's a lot more writing. So let's just do our zero product law, which means set each factor equal to 0, because if either one of these were 0, then it would still equal 0. So that means either one could be 0. All right, solve each one. Subtract 1 to the other side. Same thing here, add 1 to the other side, then divide by 2. Okay, now let's put sine x back in. Okay, so sine x goes back in, and there we go. So guess what we have now? This is really sloppy. We have sloppy writing, that's what we have now. Okay, we are going to go to the unit circle now. So we want to find where sine, which is y, I'll do this in red, y is -1, which would be down here. Okay, so that means our solution would be x equals, check your domain, we're between 0 and 2 pi, so we would call that 3 pi over 2. Okay, now let's do this one. Another unit circle. We have where sine, again, which is y, and this would be little, and it's positive. So y is positive here and here. It's little here and here, the y value. So those rotation angles would be in radians 1/6 of a pi and 5 pi over 6. So I'm hoping your unit circle skills now are up to par from the last unit, our first half of trig unit. And there we go. Notice those answers are exactly the same as what we had. So stating the general solution, we kind of already know that all three of these angles are the same distance apart. We discovered that on the last part of this example. So we'll just write that as pi over 6 then plus 2/3 of a pi times n, where n is an element of the integers. Okay, so we went through that already on the last example. All right, example number 4. Use an algebraic procedure, so not graphically, to determine the roots of the equation on the given domain and write a general solution. Okay, so on the given domain, so here's your domain given. So first we're finding a specific solution, and then they want us to find the general solution with the n pi to n pi stuff. Okay, so let's look at this equation. We have 4 sine squared a minus 1 equals 0. All right, so we have a sine squared. Yes, we do. It is quadratic, but that's the only term that has sine. So we could just isolate this. So we'd add 1 to the other side, and then divide by 4. Sorry, lost my 4. Divide by 4. Okay, then to get sine by itself, we would want to square root both sides. Okay, so that we have sine A equals square root of 1/4. Okay, first of all, it's going to be plus or minus, okay? Because we're looking for something, the 1 squared gives you 1/4, so the negative would work as well. Okay, when you have a fraction, square root the top, square root the bottom. Square root of 1 is 1. Square root of 4 is 2. There we go. All right, so sine A equals plus or minus 1/2. All right, off to the unit circle. Okay, first of all, sine, which is y, plus or minus. Oh, that could be all 4 quadrants. Okay, and you'll recognize this is little. So where sine is little would be at the 6s of a pi. Okay, now check your domain. We're between 0 and 2 pi, so we're going to name this kind of normally. Okay, and this time our angle's A. Take note of that. So A would equal, first angle would be pi over 6. Then we have almost all the way to pi, but 1 less, so 5/6. 1 more, 7/6. And then 1 less than 2 pi, which would be 12/6, so back to 11/6. Okay, if you're not remembering this, go back and review the unit circle working backwards lesson. Okay, so here is our solution for that particular domain, 0 to 2 pi. Our general solution, okay, we want to look back at our unit circle. Okay, you'll notice that these two are in a straight line from each other, so we'll be able to name those with 1. Notice they're not all equal distance apart, so we can't name it with just one particular one. But we'll start with pi over 6, and if we add just pi, we get to 7 pi over 6. So if we add pi n, we have covered therefore the first and the third quadrant terminal arms. Okay, now we'll go 5 pi over 6 plus, and again, if we add pi n, we will cover the terminal arm in quadrant 4. So pi n, where n is an element of the integers. Good, so you didn't need to add 2 pi n to all 4 of those. All right, let's take a look at the next example. That was our general solution there. Okay, tan squared x plus tan x equals 1, sorry, equals 0. And our domain is 0 to 2 pi. All right, so let's take a look at this. We have a squared and we have a tan. All right, this time we can't isolate tan by just moving that to the other side. And definitely don't divide by tan because you're getting rid of one of your solutions. So what's our first step in factoring? Because that's what we're going to have to do, greatest common factor. So they both have a tan x common. So if we factor that out, tan squared, again, remember this is just tan x and then squared, we're dividing that by tan x, so we'd be left with one of those. Divide tan x by tan x, you're left with a 1. Okay, there we go, nicely factored. And again, zero product law means either one of these factors could equal 0. So tan x equals 0 and tan x plus 1 could equal 0. Okay, this one could go a little further for solving. Tan x equals -1. Okay, that's looking good. And guess what? Now we're off to the unit circle. Okay, so where tan is equal to 0. Well, if you recall, tan is y over x, right? So in order to have 0, that means our numerator, y, would have to be 0. Where is y 0? Right here. Oh, sorry about that. Right here, right here. Okay. So let's name those. We would have our angle this time is called x, so we write x equals. Don't forget that, okay? That's important. Check your domain because this angle here, this terminal arm here, could be 0 or it could be 2 pi. So you got to make sure where the equal to signs are. And in this case, it's both 0 and 2 pi. Okay, then we have this angle, which would be pi. And there we go, our 3 answers. All right, let's try this second equation. Double the fun when you have second degree equations. Okay, so tan x is -1. Okay, so where would tan y over x have a value of 1? Well, that's when the coordinates would be the same, like when you have root 2 over 2, root 2 over 2. So first of all, negative, where is it negative? Would be, I'm just going to move this down a little bit, we're getting a little crowded. Okay, it would be negative here and here, where the signs of y and x are opposite. Where are the coordinates the same? Right smack dab in the middle for the 45s or the quarter pies. All right, let's name those. So x would equal, that would be 3/4 of a pi. And this one down here, almost all the way to 2 pi, which is 8/4. So this would be 7/4 of a pi, 7 pi over 4. Awesome. Okay, those are our specific solution answers. Looking good. Now let's come up with our general solution. Okay, so that's with the n pi stuff. When you go to general solution, it's a good idea to look back at the unit circle here that you drew and where your answers were. This is why I put dots on there so I can see where the answers were. Okay, so we're naming this generally. So it looks like it's happening at 0, pi, 2 pi, really just multiples of pi then, isn't it? Or you can start with your first one, 0, plus multiples of pi and pi, right? How do you get to the next one? Good. Now to this one, 3 pi over 4. And you'll notice these are in a straight line from each other. So again, we could add just n pi, or pi n, doesn't matter the order you write that, where n is an element of the integers. Okay, excellent. Let's see what's on the next page. All right, okay, example number 5, our last example, but I only have a minute left in this video, so I'm thinking we might finish this up in the second video. If you wanted to get started on this while you're waiting, just keep in mind for this one, it's cosecant squared x minus 3 cosecant x minus 28. And we're trying to find the zeros, so we're actually making that equal to 0 when we're finding the zeros. And we could do this graphically. We'll probably check it graphically, but initially we're going to do it algebraically, okay? They should have said algebraically in the question. All right, so we're going to replace, we're going to let cosecant x equal, say, m, and this would become m squared minus 3m minus 28 equals 0. Okay, we'll finish that up in the next video. I will see you guys then.